Okay, I'm going to talk about how to think about triple integrals. So my advice is to don't think about hypervolumes or whatever things in 4 dimensions. I would say that's just very hard to visualize, for me at least. I'm going to suggest a slightly better way. I'm going to think of it as f of x, y, z times volume, or really as dv. So I'm going to think, so sort of like, it's like an analog of 3D volume. I guess you could call it weighted. So you actually already know of a triple integral. So let me show you how to get the simplest triple integral. So it's actually a double integral. So it's actually the 3D volume. If you have some surface z of xy and you want to find the volume under that surface, then the volume is the double integral over r of z. Let's just assume the bottom surface is 0, just to make things easy. Z of xy dA, right? So these are the basically, if z was positive, this was the interpretations we were using for double integrals. But here's the catch. So you can put z into the integrand, because in fact z minus 0 is the integral from 0 to z. Let me put xy's here. Z of xy of dz, right? Because it's 1 times dz. The antiderivative of 1 is z. So you evaluate from the limits, and that's what you get there. So let's just plug this in. So volume is, when you plug this in, it's the double integral over r times the single integral of the heights. So I would say this is the base, and this is the height. Base times height is volume. And then we have 1 times dz dA. And this thing we'll call dV. That's the volume of a small cube. And so this is a triple integral. And so that's a triple integral. And I'm just going to abbreviate this as like 3dr of 1 times dv, where 3dr, it's r for your xy's, and then for your z, it's going to range from 0 to our height function z of xy. For example, this could be x plus y. It's an explicit function of y, xy. And so that's a triple integral. And so I claim then that all the other triple integrals you're just going to replace 1 with some function, f, x, y, z, to integrate. Right? So our integral over r and then 0 to z, and we have 1. We're going to replace that with this. Remember, this was dz dA. Now we're going to replace that with the integral over r times the integral from 0 to z xy. And instead of the 1, now we're going to add f of x, y, z. And everything else is the same. Right? So really, the only difference is this step here, the z integral. And so you'll have to evaluate the integral from 0 to z xy of f of x, y, z dz. with xy fixed before the dA integral. Okay, so then once we do this, we get a double integral. And this is just an ordinary double integral involving just a function of xy. And this function of xy is this thing. Whatever that thing is, it's a function of xy. And so you know how to integrate it. And it looks bad because it's kind of big, but we won't give you a problem where you can't integrate it. So after you crunch this nasty integral out in z, you will get something that's doable in xy. And so really, the moral of the story is just think of it. Don't get freaked out by the fact that it's a triple integral. Think of it first as a double integral, as a volume integral, and it's just double. And so you're just going to find your z of xy and your r limits. So for example, if this was the base of your 3D region, like let's say we had this tetrahedron, then the base is this triangle, then the base would be something like x1 minus x, for example. And that's what I mean. That these are your y's, these are your x's. You've been doing this for a week now. And so this part at least is routine. So then next, to 3Dize it, is just put z into an integral, and then finally add f. And you're just going to stick that where 1 used to be. Okay? I think if you follow this step, you can just think of it. This allows you to just use your knowledge and intuition for double integrals that you've already built up, and you don't have to relearn for everything for triple integrals. They're effectively, in my opinion, they're very similar to double integrals. Okay, thanks for watching.